Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 23, Organic Chemistry 1. Today we will start on chapter 7, Alkyl Halides, Nucleophilic Substitution and the Elimination Reactions. Halogenated organic compounds can be classified to four classes. An alkyl halide simply has a halogen atom bonded to one of the sp3 hydride carbon atom of the alkyl group, like here chloroethane. This is sp3 carbon of alkyl group bonded to halogen. An allyl halide simply has a halogen atom bonded to one of the sp3 hydride carbon atom next to the carbon double bond carbon. sp3 next to carbon double bond carbon. We call this allyl group. Okay? A vinyl halide has a halogen atom bonded to one of sp2 hydride carbon atom of alkene. So we have here sp2 of the alkene connected, the halogen connected to one of these. An aryl halide has a halogen atom bonded to one of sp2 hydride carbon atom of aromatic system, like this is sp2 carbon of aromatic benzene ring system and connected to the halogen. We call this aryl halide. So we have four: alkyl halide, allyl halide, vinyl halide, aryl halide. How do we name halogenated organic compounds? There are two ways: either IUPAC or common name. For the IUPAC, we consider alkyl halide as an alkane, and the halogen are substituent. So for the fluorine, we give it fluoro. Chlorine atom, we give it fluoro as a name. Bromine, bromo. Iodine, iodo. For the IUPAC systematic system, we first identify and name the parent, identify and name the substituent, number the parent chain and assign the locant to each substituent, assemble the substituent alphabetically. Common or trivial names are constructed naming the alkyl group followed by halide, such as isopropyl bromide. This is useful only for simple alkyl halide. Let's train. We have to give IUPAC common and say if there is nothing or none. The first compound, IUPAC, iodoethane, or common, we call it ethyl iodide, because we have here two carbons. Here, four carbons. So this is one. So 1-bromobutane. Common name N-butyl bromide. For this compound, you have three carbons. So that's 2-chloropropane. Common name, we call it isopropyl chloride. For this one, this is a long chain, 3 carbons, so that's propane. From either side, we reach the same number system, 1, 2, 3. On number 2, we have methyl and we have fluoro, but F comes first, so it's 2 fluoro, 2 methyl, propane. Common name, tertiary butyl fluoride. Tertiary butyl fluoride. For these two compounds, the first one, chlorocyclopentane. Common name, cyclopentyl chloride. For this one, we have chiral center, 2 of them. So we have to mention when we give the name. So that's 1R, 3R, 1 bromo, 3 chloro, cyclopentane. We gave 1 to the bromo because alphabetically B comes before C in alphabet. That's why we give here 1, 2, and that's 3. Do we have common name for this compound? No, we don't have. But you can use the trans for this compound, Br up and Cl down. So we have here H up and H down, and we can use this as 1 trans, 1 bromo, 3 chloro, cyclopentane. These are names for some common halogenated organic solvents. Here is IUPAC name and here is the common name. For the first one, we call it dichloromethane. Common name, methylene chloride. Here is trichloromethane. Its common name, chloroform. Here is tetrachloromethane. And we give it common name, carbon tetrachloride. Alkyl halides are classified according to the nature of the carbon atom bonded to the halogen. So if we have CH3 halogen, we call it methyl halide. Here is methyl chloride. If the halogen bearing carbon is bonded to 1 carbon, this carbon is connected to 1 carbon, we call this primary halide. Primary halide. If the carbon connected to the halogen connected to 2 carbons, then it is secondary halide. If the halogen bearing carbon is bonded to 3 carbon, it is tertiary halide. It's tertiary halide. We have also, if you have dihalogenated compound, if the halogens are on the same carbon, we call it geminal dihalide. Geminal dihalide, 2 chlor on 1 carbon, we call it geminal, from the Latin source, twin. If the halogen are on 2 adjacent carbon, we call it vicinal dihalide. 2 adjacent, 2 neighbor carbons carrying halogens, this means that it is vicinal dihalide. Let's take question. For each of the following compounds, give IUPAC, common, classify the compound as methyl or primary or secondary or tertiary halide. For this compound, the long chain but 1, 2, 3, 4. On carbon 1 we have bromo, so it's 1 bromo. 3 you have methyl, 3 methyl. Since it has that terminal, so it's iso. So it's iso with 1, 2, 3, 4, 5 carbons. So it is isobentyl bromide. And this carbon connected to only 1 carbon. So it is primary alkyl halide. It's primary alkyl halide. For this compound, the long chain 7 carbon, here is 1, 2, 3, 4, 5, 6, and 7. Of course, we have to start with this because that's 1 iodo. So it is 4 bromo, alphabet B, then C, then I. Then it's 4 bromo, 5 cyclopropyl, 1, 2 iodoheptane. There is no common name for this structure. It is primary at the carbon carrying the iodine and secondary on the carbon carrying the bromine. This is primary, this is secondary. Physical properties of alkyl halides. For the dipole moment, we have taken before that dipole moment equals charge time distance. The electronegativity of the halogen increases in this order: iodine, then bromine, then chlorine, then iodine, with electronegativity is higher. The highest is fluorine, then going down to chlorine, then bromine, then iodine. Halogen length, bond, carbon, halogen bond length. For carbon fluorine, shorter, 1.38. For CCl, 1.78. CBr larger, 1.9. And of course, carbon iodine is the largest, 2.14. That's bond length. As you can see, carbon fluorine bond is the shortest, while the fluorine electronegativity is the largest. So these two effects oppose each other, with the larger halogens having larger bond lengths but weaker electronegativities. The overall result is that bond-dipole moment increases in this order. Dipole moment of Ci is 1.28, less than the carbon bromide, which is larger, 1.48. Here we have carbon fluorine bond dipole moment 1.5, less than the chlor, which is 1.56. So the dipole moment of the iodine carbon bond less than CBr, less than carbon fluorine, less than carbon chlorine bond. Boiling points. Two types of intermolecular forces influence the boiling point of alkyl halide. The London dispersion force is the strongest intermolecular attractions. Molecules with larger surface area have larger London attraction and resulting in higher boiling point. And as we know, as we go down the periodic table, the molecular weight increases and the boiling point increases. dipole-dipole attraction arising from the polar bond of carbon halides also affect the boiling points, but to a smaller extent. Well, the melting points increase with increasing the size due to the higher van der Waals force. So the iodides, alkyl iodides, will be higher in boiling points than alkyl halide, which is higher than chloride than fluoride. Again, the boiling points of the isomeric haloalkanes decreases with increasing in the branches, okay, as the surface area decreases and the van der Waals force decrease. So if you have a butyl, 1, 2, 3, 4, butyl chloride will be higher than isobutyl than tertiary butyl. Okay, this one will have the higher boiling point because the van der Waals will be higher interaction force. Densities. Alkyl fluorides and alkyl chlorides, those with just one chlorine atom, are less dense than water. Alkyl halides with 2 or more chlorine atoms are denser than water. And all alkyl bromides and alkyl iodides are denser than water. Once again, alkyl fluorides and alkyl halides with only one atom are less than water. Alkyl chlorides with 2 or more chlorine atoms are denser than water. That's for the chloride. On the other hand, all alkyl bromides and alkyl iodides are denser than water. Okay. Now, when water is shaken with hexane, the two liquids separate into two phases. Which compounds is present in the top phase? That's separating funnel, and this is a two layer. Of course, the one with less denser will be the up. So hexane will float on water layer. So in case of hexane, that will be hexane up and water down. That if we shaken with chloroform, CHCl3, density is 1.5. So in this case, the water will be up and the chloroform will be at the bottom. Water will float on chloroform of density 1.5. Reactions of alkyl halides. Alkyl halides can undergo two major types of reactions: substitution reaction and elimination reaction. In substitution reaction, nucleophilic substitution, called by this name because the electrophilic alkyl halide forms a new bond with the nucleophile which substitute or replace the halogen at the alpha carbon. So we have nucleophile and we have here alpha carbon carrying the halogen. That the substitution will be the reaction replacing the halogen with the nucleophile. And the halide will be leaving group. The elimination reaction. The reagent reacts as a base, abstracting a proton from the beta carbon of the alkyl halide. Recall, most nucleophiles are also bases and halide leaves. We call this reaction dehydrohalogenation reaction. Dehydrohalogenation reaction. So, base will take proton, 2 electrons here will move to form double bond, and the halide leaves. This is dehydrohalogenation reaction. This is the beta position. Let's discuss the substitution reaction in more detail. Possible mechanism for substitution reaction: second order nucleophilic substitution, we call it SN2 reaction. The reaction takes place in a single concerted step، يعني في خطوة واحدة. A strong nucleophile attacks the electrophilic carbon, forcing the leaving group to leave. Nucleophile attack the electrophilic carbon and the leaving group leaves via transition state, and this is the product. The order of the reactivity of substrates: methyl halide faster than primary, faster than secondary alkyl halide. Alkyl halide, tertiary alkyl halide cannot react by this mechanism. The tertiary do not react by this mechanism. The rate of this reaction directly proportional to the substrate concentration and the nucleophilic concentration. So rate is equal to K constant, concentration of substrate times the concentration of the nucleophile. That's why we call it second order. One in here and one in here, the sum is 2. So nucleophilic attack, loss of leaving group. If you look for the reaction diagram, the energy, this is the starting material, and when the nucleophile attacks and the bromine goes out, that goes through what we call a transition state. That is the structure of transition state, higher in energy, and then goes to product. One step concerted mechanism reaction energy diagram. Under certain conditions, the reaction of 0.5 molar 1-bromobutane with 1 molar sodium methoxide forms 1-methoxybutane at rate of 0.05 mole per liter second. What would be the rate if 0.1 molar of 1-bromobutane and 2 molar sodium methoxide were used? We know that this is really the rate equation. The rate equal rate constant times concentration of substrate times concentration of the nucleophile. We have given the rate, we have given the concentration of the substrate, and the concentration of the nucleophile. So we can get the rate constant, or rate. Here is the rate, concentration of bromobutane, concentration of methoxide, so we can get the K. Now we get the K, apply the new rate. Okay, here is K, concentration of the bromobutane, the new concentration of the methoxide. It's just very easy, direct application in the rate equation. And the new rate will be 0.02 mole per liter second. Consider the reaction of 2-bromobutane with sodium hydrosulfide. 2-bromobutane with sodium hydrosulfide. This is secondary alkyl halide, so we can expect that this reaction goes through SN2 mechanism, the sulfide attack with elimination of bromide. This is a transition state. This is linking. This is going out. This is a transition state and higher in energy. Br is out and S is linking to the carbon, so this is a new product, and Br is out. Here is a model, or I call it a map, okay, chemistry map for the reaction of alkyl halide. Like primary alkyl halide will react with hydrosulfide to form thiols, with methoxide to form ether, that's methoxyethane, with hydroxide to give alcohol. Just we take Br out and replace that with a new nucleophile. React with amine to form primary amine to form secondary amine, with cyanide to form nitrile, with carboxylate to form ester, with triphenylphosphine to form ethyl triphenylphosphonium bromide, with acetylides to form pentine, 2-pentine, with azide to form azidoethane, with alkyl sulfide to form sulfane. All what you have to do is, this is a primary alkyl halide, and I decide, okay, I examine and predict this is a nucleophile, this is a nucleophile, this is a nucleophile, this is a nucleophile. So what you have to do, break this bond, take the Br out, and make a link between the nucleophile and this carbon. And you get it. Halogen exchange reaction. The reaction provides a useful method for synthesizing alkyl iodide and fluoride, starting from alkyl chloride or bromide reacting it with potassium iodide. In presence of acetone, you get alkyl iodide. On the other hand, you can react with alkyl halides, chloride and bromide, with potassium fluoride. In presence of 18 crown 6 in acetonitrile, you get alkyl fluoride. See you in the coming lecture. Bye bye.